Okay, I want to use some things we've learned now about zeros and end behavior to actually graph polynomial functions in the xy plane. And the first thing I want you to realize is polynomial functions are continuous. In other words, um, there are no breaks in the graph. And furthermore, they're smooth. Okay, they're kind of hilly. There's no sharp edges here. Okay, so that's important to realize. Now, I will start with the first example that we'll graph, and we'll first understand the end behavior and the zeros, and then we'll use that information to transfer it to a two-dimensional graph. Okay, so we have a polynomial function here, and I want you to notice that this is the factored form. This is completely factored. That's very handy when you go to graph these. For example, I can already tell if x is 1, 1 minus 1 is 0, and 0 multiplied by all this stuff gives me 0. So if x is 1, y equals 0. So that's really easy to tell whenever this is in factored form. And so for it to be in factored form, you notice how all of these are x to the first inside the parentheses, and there's no number in front of the x, no coefficient. Okay, so that makes it really easy to sort of graph. So the first thing you'll want to do when graphing a polynomial is get it into the completely factored form. Okay, so you'll have to know quite a bit about factoring. Okay, let's get started here. I'll start with maybe the ends of this polynomial. The ends of the polynomial are dependent on the leading term. And of course, the leading term is what you get if this was all multiplied out, if it was simplified, if there were no parentheses. So the leading term here would be what you get if you multiply -6 by the x squared by the first term inside these parentheses, which is x to the first, by the first term here, which would be x to the third, by the first term here, which would be x to the first. And of course, that is -6, x to the seventh. Now, x to the seventh is x to an odd power, which usually looks like this on the ends, but we're multiplying that by a negative number. I'm not worried about the 6. That's not really important. Just it's a negative number, so this now is going to flip over this way. The right end is going to go down instead of up, and the left end is going to go up instead of down. Okay, so I already know what the ends of my graph look like. Now I need to figure out when this function is positive, negative, and 0. So I will do that with a number line as soon as I know what x values make it 0. So first of all, the factors of this, the x factors are x, x minus 3, x plus 4, and x minus 1. So the x values that make those four things equal 0 make the whole function equal 0, make y equal 0. So I'm going to figure out where that happens. So x equals 0, x minus 3 equals 0, x plus 4 equals 0, x minus 1 equals 0. And again, these are the zeros. Of course, 0 is one of them. If I solve this for x, I get 3. Solve this for x, I get -4. Solve this for x, I get 1. So those are the values that make my function 0. So I'll set up my number line now. And these will be x values, right? X equals, x equals, x equals, x equals. So I need to list -4. I need to list 0, that's the next one. I need to list 1, and I need to list 3. Okay? And at those x values, the whole right side is 0. And since this is a function, y equals 0. So what I'm going to do now, I've got my x values listed. I need to list my y values because I'm trying to graph this in the xy plane. So I'll put y up here. So if x is -4, y is 0. So see, I'm going to list all my y values up here above. And similarly, y is 0, 0, 1, and 3. Okay? Now, y is going to be positive or negative in each of the regions between those x values. So what we'll do is actually, I'm going to use my ends to help me get started. I know the right end of my graph goes down forever, so that means the right end of my graph has to be negative. You see how I avoided plugging any numbers in to this to figure that out? I know the left end of my graph goes up forever, so the left end of my number line, my y values have to be positive, right? Y is positive if I'm going up forever. And now I will use the number of sign changes. -4 has 3 sign changes, right? Because it came from the x plus 4. So 3 sign changes, SC. 0 came from the x, which has 2 sign changes. 1 came from the x minus 1, has 1 sign change. And 3 came from the x minus 3 to the first, which has 1 sign change again. I know whenever there are an odd number of sign changes, the previous sign changes. And when there's an even number of sign changes, my sign is the same on each side. So plus has to be different than what's here because there's an odd number of sign changes. So this is a minus. An even number of sign changes, they have to be the same. An odd number, they have to be opposites. And an odd number, they have to be opposites. So see how this ended up working out? If this would have been a plus, I would have known there would have been a problem since the sign should have changed. But it didn't, so I'm guessing that I've done everything correctly so far. Now I'll use this information, the ends up here, and I'll use my positive and negative y values and my x values to graph. And this process gets really fast when you practice a little bit. So I'm going to label my important x values, which are my zeros of -4, 0, 1, and 3. And I know y is 0 at those, so here they're going to be on the axis, right? If y is 0, I'm on the x-axis. So maybe I'll write that here. This means on the x-axis every time y is 0. If y is positive, I'm above the x-axis. Sorry I'm writing so small. If you can't see it very well, I'm telling you what I'm writing, so you could just write that. And if y is negative, you're below the x-axis. Okay? So on my left end, I already know it looks like this blue region here, so I'll go ahead and graph that. And on my right end, I know it looks like the yellow region there, so it looks like this. And now I just use all my signs in between here. So between -4 and 0, y is negative. So I'm below my x-axis, and I have to connect my 2 points on the ends. From 0 to 1, I have to connect those 2 points, and I have to be below the x-axis, so I dip below again. Be careful not to have a sharp edge here, right? Because as I mentioned when we first started this, polynomials are smooth. They don't have sharp edges. From 1 to 3, I have to connect those points, and I have to be above the x-axis. And this is the graph of this function. Now, lots of times someone will ask, well, how far down do you go below the x-axis here, for example? Well, if you want to know that, plug in a number between 0 and -4 for x. Plug it into the function and get your y, and you'll see how big it is. But we're more interested in the general behavior. Is it above or below the x-axis, basically? And that's our first example here. Okay, I'm going to get you started on another example, but I won't quite have time to finish it. Okay, so in this function, this is not completely factored. It's close, but here we have a number in front of this x, so we need to factor that -3 out of that. So if you go off to the side and look at -3x plus 2, and you're trying to factor the -3 out, a lot of people don't think you can factor a 3 out of a 2, but you can. You just end up with a fraction. So when you factor -3 out of -3x, you're left with x, right? And the reason for that is you're dividing by -3 when you factor out a -3. So 2 divided by -3, hey, that's -2/3. So that's what goes here. So what you're left with is what you get when you divide these things by what you're factoring out. So I can rewrite my function now. I'm just going to replace this with its factored form. And now I'm just going to rearrange things, right? I have an x minus 2 to the x minus 2/3 squared here, And if I multiply that by another one, those are going to be cubed. And then I have a negative here that I can multiply by this -3 to put my constant in the front, which is going to give me +3. And then I've got my x plus I and my x minus I. Now it's completely factored. You could look at the end behavior, which will be 3 times x to the third times x, which is 3x to the fifth. So the ends will look like 3x to the fifth. You could figure that out. And your zeros will simply be 2/3, -I, and +I. Now, these are not real numbers, so they're not actually going to be zeros on our number line. Our number line only represents real numbers. So this will be the only zero on our number line and in our graph. And then you'll find the signs of each region and use all of this information to graph this polynomial.